LeetCode problem number 684, redundant connection. So this problem is a bit tricky. It gives us a description of a tree, which is a undirected graph that is connected and has no cycles. So this is the important part. And here we are given a graph that started as a tree with n nodes labeled from 1 to n. So for example, over here, you can see nodes 1, 2, 3, and was not an edge that already existed. So here it gives us more information about the array, the edges array, and yeah, it just explains what A, B is, indicating there's an edge between nodes A and B. So our goal is to return an edge that can be removed so that the resulting graph becomes a tree. Right? It won't be a cycle anymore. And if there are multiple answers, we have to return the answer that occurs in the last input. So for example, here 1, 2, and so these two have formed an edge, and for 1, 3, this will form an edge. And now for 2, 3, since we don't really need this edge here, because with the first two it has formed a sufficient tree, and adding this edge will make it a cycle, which is the edge we have to return, indicating that this is a redundant connection. So to solve this problem, we will have to use union find. Obviously it's not mandatory, but using union find will achieve the best performance. So what union find basically does is, let's say I use this example. So what my union find will do is let's look at the code first. So here I'm constructing a parents vector which is of the size plus 1, the total size which is 3 plus 1. So this will be 4. This will be 4. And then for the tree size, it will be the same as well, but constructed with default value of 1. And this IOTA function basically makes the value increment in the vector. Yeah, that's basically what this function is for. So what my union find would do is, let's say I will have each node. Let's say for this case we have 1, 2, and 3. So for each node, the parent will be itself. So the parent will be itself, right? And the size of each node, which in this case can be considered as a tree as well, only consists of one node, right? So when I parse the first edge of 1, 2, I will connect the 2 into 1, like so. So this means that 2 is a child of 1, which is a parent. So what that happens is my parent of 2 will change to 1, and now the tree size of the first node will now turn to 2, right? Same thing with 3. When I'm parsing the second edge, parent will turn to 1 as I connect this as a child. This will turn into 3 now instead of 2, right? Because this tree, right, if I redraw it, will look something like this. This is a valid tree, and this tree consists of 3 nodes, right? After that, if we take a look at the third edge, connection 2 and 3, if we both look at the parents for 2 and 3, they are the same, right? If they are the same, we return false, which means that this edge is the one that we will need to return, because this edge, if you notice, is the one that will make the it is the redundant connection that will make our tree into a cycle, right? So now that I've explained how it works, let's show how it works. So we look here, I have a for loop and A and B. So A will be the first number, B will be the second number of the edge. Then I throw it inside my solve function. So let's say parent 1. We'll try to find the parent of the current edge 1, right? In this case, if you take a look at the find parent function I have here, it's a very straightforward function. So if n is not a parent of itself, then it will search recursively. Otherwise, it will just return the current parent. So in this case, for 1, right? So if you remember, a is 1. Over here, a is 1. So 1 is not equals to parents 1. So parents 1 is 1 and 1 is 1. So basically this does not trigger. It will just return 1. Same thing with parent 2. I'll save the trouble, and parent 2 is equals to 2. Right. Okay. Here I compare the tree sizes. So what we want to do is we want to merge the tree that is smaller into the tree that is larger. So here I'm comparing the tree sizes, and since they are the same, we will run this else statement, which parents 1, 1, this number will equal to parent 2. Right? So parent 2 will be 2. In this case, my code is doing the opposite way. Just now I showed you that 2 is a child of 1, but now my code, in this case, will make 1 the child of 2. In a way, it still works the same way, so don't worry too much about this. But yes, now the parent of 1 has now become 2. Right, it makes sense. Let me draw it out. Right, so the parent of 1 has now become child of 2. Right. Okay. After that, once this is done, we return true. We only check if it returns false, which means that the parents are the same and we have a redundant connection. In this case, it is not. So we move on to the next edge, which in this case will be 1 and 3. So let me type out 1 is equals to a equals to 1, b equals to 3. So the parent, so in this case n is 1. And if you look at 1 is not equals to parents 1, right? Because its parent has changed to 2, right? So now I replaced parents n with find parents n. Let me do some recursion here. So n is equals to 1, as I mentioned, and since n is not equals to parent 1, which is 2, so 1 is not equal to 2, so our parents is equals to the recursion of parents n, and parents n is 2. Right, so n is equals to 2 now, and since 2 is equals to 2, right? So this is a trigger, and you return 2. You return 2 over here. So parent 1 basically become 2. Okay. So that's what this find parent function does, right? No need to stress too much about this, but we do the same for parents 2. So n is equals to 3, right? We're putting 3 inside, and since for 3 not equals to parents 3, 0, 1, 2, 3, and since they are the same, this if statement is skipped and we just return 3. Parent 2 is 3. Okay, we do the same thing over here. Okay, just now I forgot to increment the tree size of parent 1, or of parent 2, sorry. 2, right, increment with 1. Okay, let's continue. Yeah, so this increment was for our node 3 or node 2 has now became a tree of 2 nodes, right, of both 1 and 2. Okay, so if we continue, if the tree size of parent 1, which is 2, is more than the tree size of parent 2, which is 1, which in this case it is, so parents 2 is now parent 1, which is 2. Right. So we have shifted the parent of 3 to 2. And then we increment again. We increment this to 3, and then we return true. Let's look at the third edge, which is 2 and 3. So here, if we find our parent, so n is equal to 2, and is not equals to parents 2, so 0, 1, 2. Since it does equals to, we can just return it. Now for our second parent, n is equals to 3, and 3 is not equals to parents n, which in this case, parents n 0, 1, 2, 3 is 2, so we have to replace, and is equals to find parents n, which is 2. And since we know what happens to 2, basically they are the same, so this returns as 2, and this as 2. Okay, now if you look here, both parent 1 and parent 2 are the same, meaning that node 1 and 3 have the same parent, and if we were to introduce this edge, it will create a cycle, which is not what we want, which was why we return false. And when we do so over here, we return false, we will return the edge as well, right? So return A and B, which is the last edge that occurred in the input. Okay, yeah, that was a mouthful, but that's basically the algorithm. That's all I have to show. Thanks.